Hello students, welcome to the class. So today we'll be seeing theory part 13 of the chapter 6 equilibrium, in which we will be covering NCERT section 6.13. So this is the disclaimer. Now in this class our objective would be to look on the effect of common ion on solubility. Then we will see a way to calculate pH. We have already dealt with this pH thing, but in most of the cases you will find it difficult to calculate the pH because of the complexity of the scenarios that you will handle. Therefore, in a way, I am going to give a trick for this pH calculation. If I talk about the specific sections of the NCERT that we will be covering, then it would be 6.13.2, which is common ion effect on solubility of ionic salts. And as I said, we will be seeing a trick to calculate pH. So let's start with the common ion effect on solubility of ionic salts. Now, it is generally seen that a solubility of the ionic salts decreases due to the common ion effect. We can explain this on the basis of Leach-Atterial principle. So first of all, the concept says that if you are having a sparingly soluble salt and you add a common ion, which is common in the sense with respect to the sparingly soluble salt, then there will be increase in the product concentration. Therefore, reaction will go back in the backward direction, and this whole thing will happen due to the Leach-Atterial principle. As a result, we will see that the solubility of the salt is decreased. We can take the example of silver chloride to explain the same. So in this silver chloride solution, we are adding sodium chloride. You know it very well. Sodium chloride is having a higher solubility as compared to AgCl. Now, initially we have this equilibrium state where we have AgCl dissociated to form Ag plus aqueous ion and Cl minus aqueous ion. Now the dissociated and the undissociated part are in equilibrium. If we add NaCl, as I said, is a strong electrolyte, it will dissociate completely, and due to its high solubility, it will provide a high concentration of chloride ion that will act as a common ion, because AgCl has this chloride ion as well as sodium chloride also has this chloride ion. We know that sodium chloride is highly soluble, so it will not precipitate back. But the sparingly soluble salt, which is AgCl, it will precipitate back. And as a result of this Leach-Atterial principle, the equilibrium will shift towards the left side. Now, what would be the result of this backward shift? So first, you will see that the AgCl is precipitated more and more. Means the solid form of AgCl is seen in the solution phase. Then the concentration of Ag plus will also decrease, because to make AgCl we need Ag plus. So the Ag plus will be consumed in the backward reaction. As a result, we will see a less concentration of the same. Further, we can just conclude the final saying that our solubility of AgCl is reduced upon the addition of a common ion, which in this case is the chloride ion coming from the sodium chloride. Okay, so solubility, which is S, so that S is reduced. The value of that S is reduced. Now we will see the trick for pH calculation. To understand this trick, first you have to be aware about the normality. It is very simple to understand normality. In that understanding, we need to understand first of all equivalence, which is basically the amount of substance that react with 1 mole of another substance. Suppose you are doing a reaction, then you will have two molecules which will be reacting in most of the cases. I am not talking about the dissociation reaction, but in most of the reaction what you will see that two species are there which are reacting with each other. Now, if you are considering one of the species and you are trying to calculate the amount of that species which will be required to react with 1 mole of the another species, that amount is called as the equivalence. Okay. Further, if you want to define normality, then it is the number of these equivalents which are present per liter of solution. Okay. Suppose I say that 12 gram of species A react with 1 mole of species B. right? So 12 gram will be the equivalence. Further, if I say that 24 grams of this species A is present in your solution, then what will be the normality? How many number of equivalents are there? So 2 equivalents are there per liter of the solution. Okay, so 2 divided by 1, it will give you your normality. As simple as that. But in case of this acid-base reaction, which is the case of ionic equilibrium, we have a specific condition. So to define that specific condition, we will limit the n factor. We will try to understand. It's a new term. Don't get confused with this normality. Once you got the formula with relevance to the n factor, you will find it very easy to understand. Now, how do we define this n factor? It is the number of equivalents per mole of that substance. So basically here we are defining it in terms of per mole. And in terms of this acid-base reaction, we will consider that how many H plus and OH minus your given molecule can donate or accept. So that will be the n factor. How? Let's take some examples here. So here we have hydrochloric acid, sulfuric acid, phosphoric acid, sodium hydroxide and calcium hydroxide. The top 3 one, which are your acids, they are mono, di and triprotic. Means they can donate 1H plus for HCl, 2H plus for H2SO4 and 3H plus for H3PO4. Therefore, their n factor will be 1, 2 and 3 respectively. Because they can donate 1H plus for HCl, 2H plus for H2SO4 and 3H plus for H3PO4. So they will have an n factor of 1, 2 and 3 respectively. If I talk about the base, then we will talk in terms of acceptance of H plus. Here your sodium hydroxide can accept 1H plus due to the presence of 1 OH minus. Therefore, it is having n factor value as 1. What about calcium hydroxide? It has 2 hydroxides present. So each hydroxide can accept 1 H plus each, contributing to total of 2. Therefore, the n factor for this calcium hydroxide will be 2. Now, if you are well aware about this n factor, then we can put upon the formula of normality. It's very simple. So it is in terms of molarity and given by n is equals to molarity multiplied by n factor. So if you are trying to calculate the normality of a given solution, which is acid base type, in that case first you will calculate what? M, where M will be your molarity and N will be your normality, which is equivalents per liter, and finally we have this NF, which is your n factor, right? So this is number of equivalents per mole. Now we already know how to calculate this equivalent. It's very easy. You just have to see whether your acid is giving 1 proton or 2 proton or 3 proton, and that will correspondingly give you the n factor value as 1, 2 and 3 respectively. Okay. Further, we can just rearrange this formula by putting the value of molarity. So what is molarity? It is the number of moles per liter of the solution. If we denote moles in with the help of N and volume with the help of V, then the above formula can be written as normality is equals to N by V multiplied by NF. Or we can just rearrange this to get the formula for equivalence. It's very simple. Just take the product of normality and volume and it will give you your equivalence, or it can be written in terms of number of moles and n factor. Now this formula is the most important one and we will use it to and fro in the upcoming slides. So it is basically the formula for equivalence. You can consider this as a contribution coming from each species. So if you are able to calculate the equivalence of a given species, then you will be able to calculate the contribution from each species in the given specific reaction. Now if this is clear, then we can arrive at two cases. First is, you have a solution of acid and base, and in that solution your acid or your base, anyone is present in excess. Second one, is where your acid and base are present in same normality, or you can say they are present in same equivalence. Okay. Further, we can just take the first case and try to see that in the first case what will be the concentration of the excess acid or excess base. Apart from this, we will also see that the neutralized part, which is converting into the salt, what is the concentration of that salt. For that, let us assume that Na and Va is the normality and volume of acid. Further, Nb and Vb is the normality and volume of base. Then if I try to calculate the equivalence of acid, then it will be Na into Va. We have already dealt this formula, N into V. Similarly, for the equivalence of base, it will be N into Vb, Nb into Vb. Now, if the reaction goes on and you have to calculate that what contribution from acid is in excess, it's very simple. So, the amount of acid which is being neutralized by the base, so that will be subtracted from the acid contribution. So, NaVa minus NbVb. So, this is your excess amount. Now, if I tell you that what is the concentration, it's very simple. If I am talking about the salt concentration, since your base is present in minimum amount, so it will be wholly converted into the salt, and now the salt's equivalence is equals to the base equivalent. So NbVb will be equals to the salt's equivalence, and when we will divide this thing by the volume, total volume, which is volume of acid plus volume of base, then we will get the concentration of salt. What about the excess H plus? So we know that the excess contribution from acid is NaVa minus NbVb. If we divide this thing by the volume, again we will get the concentration. I hope you are getting my point. So we are calculating what? We are calculating the excess H plus and the concentration of salt. Now why I am telling it as excess H plus? Because this is the point of telling it as contribution. Because an acid can what it can contribute? It can contribute H plus. So we can say its contribution in terms of H plus also. The number of, I would say the concentration of H plus would be the contribution from the acid. Similar. Next, we can take the case of base also. Suppose his base is present in excess, then what will happen? Let us assume first of all that NaVa be the normality and volume of acid, and again NbVb is the normality and volume of base. Then we can say that the equivalence of acid will be NaVa and the equivalence of base will be NbVb. If the base is present in excess, then the excess equivalence of base would be NbVb minus NaV. So this would be giving you the extra base contribution. Now if you calculate the concentration of salt, here we have acid present in the limiting form. So the amount of acid will be the amount of salt. Therefore, we can write the concentration of salt as NaVa divided by the new volume, which is Va plus Vb. We can just calculate the concentration of OH minus also, because here we have base in excess, right? So that excess base will give you greater amount of OH minus. So the contribution is simply directly related to the OH minus. If you calculate the concentration of OH minus, you will get the contribution from base as well, and this will be given by excess base equivalence divided by the new volume. I hope you are getting this point. So this is the first case. Now let us look on the second case. In the second case, we are assuming that acid and base both are present in equal normality. As a result of that, what will happen? All of the acid and base will be reacting to give you only salt. Okay, it will give you salt only. Suppose if you want to calculate the concentration of salt, how we'll do it? So we will suppose that NaVa is the normality and volume of acid, NbVb is the normality and volume of base, the equivalence of acid is NaVa and the equivalence of base is NbVb. Then what would be the concentration of salt? Since every ounce of salt is converted into of acid is converted into salt. Therefore, the equivalence of acid will be the equivalence of salt. So NaVa by Va plus Vb will give you the concentration of salt. Similarly, you can calculate it from base as well, because the base is also wholly converted into the salt. So NaVb divided by Va plus Vb. Now, if you get this point, we can move on to the tricky part. First of all, we have this flow chart for different cases. 3 scenarios are possible. In the first scenario, we have only one species, either strong acid, strong base, or weak acid, weak base. So the second case, we have 2 species, but they are non-reacting, means both are acid or both are base. So yet 4 cases can arise. So either you can have strong acid, strong base combination, means I am saying that we are having 2 strong acids or we are having 2 strong bases. In the third scenario, we can have weak acid and weak acid, and in the fourth scenario, we can have weak base and a weak base. So these are the 4 scenarios that are possible for 2 non-reacting species. What about 2 reacting species? So here you have to take 1 acid and 1 base, so they can be weak and strong both. So keeping that in mind, 4 combinations are possible: strong acid, strong base, weak acid, weak base, weak acid, strong base, and strong acid, weak base. Remember how you will define reacting and non-reacting species. So if they are acid and base, then they will react. If they are of similar type, like if we are taking 2 acids or we are taking 2 bases, okay, then they will not react. Remember, if you are taking 2 acids, then both of them should be strong or both of them should be weak. If you are taking 2 bases, then both of them should be strong or both of them should be weak. This should be followed. So first, the case 1 is here. So we have only one species present in this. Now in this case, we are supposing that NaNBA is the normality and volume of acid, whereas NB and BB is the normality and volume of base. Then we can have 4 cases further, starting from strong acid, strong base, weak acid and weak base. In the strong acid case, we will use the normality. Why? See students, normality is what? It is the contribution. Now, an acid can contribute in which way? Simply you can say it can contribute by donating H plus ion. So in a way, the normality is nothing but the H plus concentration, right? Further, if you want to calculate the pH from here, you will simply take the negative logarithm of this Na. What about the base? In the case of base, Nb, which is the normality of a base, will be the hydroxide's concentration, and the negative logarithm of that Nb is your pOH. But you need to calculate the pH, so we'll subtract this thing from the 14. Coming on to the third one, we have weak acid. You know the formula for weak acid? It is root under K into C. Now in place of C, we will put the concentration, which is Na, and to calculate the pH, we will take the negative logarithm of this. Now negative logarithm of this root under K dot Na will give you pKa minus log Na, because negative logarithm of Ka is nothing but pKa, and when we are having a scene where we have a square root, then that power will go to the multiplication part. So 1 by 2 is multiplied here. So this is the basic rule for using the log, right? Moving on to the weak base, similarly we can write it as pH is equals to pKb minus log Nb. So it's simple. Then the second case is when the 2 non-reacting species are present. Again we will consider Na1, Na2 are the normalities of 2 acids, Va1, Va2 be their volume, or if we have only base present in the solution, then NB1, NB2, VB1, VB2 are the normalities and volumes of the 2 bases. In this case, we can have 4 further subparts. The first is presence of 2 strong acids, second is presence of 2 weak acids, third is presence of 2 strong base, and fourth is presence of 2 weak base. When there are 2 strong acids present, we will simply take the contribution from each acid. So Na1, Va1 from the first one plus Na2, Va2 from the second one add both of this contribution, divide by the new volume, which is Va1 plus Va2. So this will give you your H plus concentration. Further, if you take the negative logarithm of this, then you will be able to calculate the pH. What about the case of weak acid plus weak acid? Here you have to remember a very important formula. For calculating the H plus concentration, it is given by root under K1, the concentration of first acid plus root plus K2 multiplied by the concentration of second acid. How do we calculate the new concentration? After dissolving two acids which are weak together, you will take the contribution from the weak acid, first weak acid, and divide it by the new volume. Similarly, you will take the contribution from the second weak acid and divide it by the total volume. Similarly, we can have the case of two strong bases. In that case, the pOH will be negative logarithm of NB1 VB1 plus NB2 VB2 divided by VB1 plus VB2. Then we will subtract this thing from 14 to get the pH. And the case is similar for weak base and a weak base. Similar to the weak acid and the weak acid, it is root under Kb1 C1, where C1 is the new concentration of the weak base, plus Kb2 C2, where C2 is the new concentration of the second base. You will take the negative logarithm of this whole thing and subtract this thing from 14 to get the new pH. Moving on to the case 3, where we have two reacting species. First, we have taken acid and base as strong, and in this we are considering that NaBa is the normality and volume of the two strong acid, and NbVb with the normality and volume of two strong base. Further, if we have three conditions, first is both have equal contribution, acid and base. In that case, we will form a salt, we will be forming a salt, and that salt will have a neutral nature because the cation and anion of the salt is coming from a strong acid and a strong base. So there will be no case of hydrolysis. What about the case where we have excess acid? In that case, we will simply calculate the remaining H plus concentration after the neutralization. So you will have some excess acid after this neutralization, and that can be calculated by using the formula NaVa minus NbVb divided by the total volume Va plus Vb. You will take the negative logarithm of this whole thing to calculate the pH. In the third case, we have excess of base. How do we calculate the excess base contribution? NbVb minus NaVa divided by total volume, which is Va plus Vb. Then further, we take the negative logarithm of that to calculate pOH and subtract it from 14 to get the pH. Moving on to the next part of the two reacting species. In this case, we have weak acid and a strong base. Suppose that NaBa is the normality and volume of that weak acid, whereas NbVb is the normality and volume of strong base. Now here is the most important part. In the first case, where all of the acid is being utilized to take up the base, but still you are left with some amount of acid, it means excess acid is present, and that excess acid is a weak one. So we have two things. Due to neutralization, we will get salt, and due to excess weak acid, we will get a weak acid concentration. So we have some salt and we have a weak acid. You know this combination. So this is your buffer solution. How do we calculate the concentration of that excess acid which is left after the neutralization? So that will be NaVa minus NbVb, contribution from acid, divided by the total volume. What about the salt's concentration or the conjugate base concentration? So both are same. So that would be simply the contribution of base divided by the total volume Va plus Vb. So pH will be pKa plus log A minus by Ha, where you will put this given values to calculate the pH in this buffer, and this buffer is an acidic one. Next case, we have similar contribution from acid and base. In that case, you will form a basic salt because the base is strong, and since it is a basic salt, and that salt is basic due to the hydrolysis part. Now remember, how do we calculate the pH in this case? It's very simple. You will use the formula 14 minus half pKw minus pKa minus log C. Then the third case is the easier one. You have excess of strong base. In that case, you don't have to worry about the buffer formation or the salt hydrolysis. You will simply calculate the extra hydroxide concentration by First, calculating the excess base left divided by the total volume. Further, you will take the pH by taking 14 minus log of this, 14 plus log of this whole OH minus concentration. Now, why are we getting here a plus? Because first we take minus log of this OH minus, right? Then we subtract it from 14. So 14 minus log of OH minus will give you 14 plus log. Okay. Then we have the third case of a weak base and a strong acid. So we just have reversed this situation. Now in that case, we will consider NaNBA is the normality and volume of the strong acid. NBBB is the normality and volume of the weak base. If we consider excess weak buffer, okay, we have excess base, then it will result in a buffer solution, and that also a basic buffer. How do we calculate the excess base concentration now? That would be NBBB minus NaVA by VA plus VB, right? Further, what will be the BH plus concentration? It will be NaVA by VA plus VB. So this is the conjugate acid concentration or the salts concentration. To calculate the POH, we will simply take pKb plus log BH plus by B concentration. So this is the Henderson-Hasselbalch equation, and further we will subtract it from 14 to get your pH. So this was your POH and this is your pH. Then next we have equal concentration of both or equal contribution of both, which will result in the salt formation. Okay, and to calculate the pH, we will use the salt hydrolysis formula half, then in the bracket pKw minus pKb minus log C. Lastly, if we have excess acid, which is a strong one, in that case, to calculate the H plus concentration, we will simply take NaVA minus NBBB divided by VA plus VB. Now pH will be minus log of this whole excess H plus concentration. Moving on to the last situation where we have a weak acid and a weak base. Suppose NaVA be the normality and volume of the weak acid and NBBB be the normality and volume of the weak base. If we are having the excess acid, then in that case, first we will calculate the excess acid concentration and we will calculate the conjugate base concentration or the salts concentration. After that, we will use the formula of buffer. So this will be acidic buffer due to the presence of excess weak acid. So pH will be equals to pKa plus log A minus concentration divided by HA concentration. If both are present in equal amount, then we have a salt of weak acid and weak base. And to calculate the pH, you have to use the formula half pKw plus pKa minus pKb. Moving on to the last case of this weak acid and weak base. If we again consider NaBA be the normality and volume of the weak acid and NBBB be normality and volume of the weak base, then to calculate the POH, how do we do it? We'll simply take the buffer solution. Why are we taking buffer solution? Because after neutralization, we will be left with a salt and some concentration of this weak base. So first we'll calculate the concentration of this excess base, which is NBVB minus NaVA divided by VA plus VB, and then we will calculate the concentration of conjugate acid, which is NaVA divided by VA plus VB. Finally, we will calculate the POH using the Henderson-Hasselbalch equation and subtract it from 14 to get the pH. So this was all from my side. Thank you for joining the session.